Hello students, I'm Dr. Muhammad Yasin. It is the first lecture about alkanes. Alkane is the part of the syllabus of Fundamental of Organic Chemistry code Chem 1113. Today we are going to discuss the alkanes, the physical and the chemical properties of the alkanes and some of the chemical methods used for the preparation of alkanes. What we will discuss today is discussed in the coming slide. Today we are going to discuss what are the organic compounds. We will discuss the brief history of organic compounds, how these were first prepared in the laboratory. We will also discuss what are the functional groups. We will then discuss the alkanes and followed by a brief introduction to the nomenclature of alkanes. Then we will discuss the physical properties of alkanes, and at the end of this lecture we will discuss the synthesis of alkanes. In chemistry, organic compounds are generally any chemical compounds that contain carbon. Due to carbon's ability to catenate, millions of organic compounds are known. To study the properties, reactions and synthesis of organic compounds comprises a discipline known as organic chemistry. For historical reasons, a few classes of carbon-containing compounds, for example, carbonates and cyanide salts, along with handful of other exceptions, for example, carbon dioxide, are not classified as organic compounds and are considered inorganic. Other than just name, little consensus exists among chemists on precisely which carbon-containing compounds are excluded, making any rigorous definition of an organic compound elusive. Although organic compounds make up only a small percentage of Earth's crust, they are of central importance because all known life is based on organic compounds. Living things incorporate inorganic carbon compounds into organic compounds through a network of process called the carbon cycle that begins with the conversion of carbon dioxide and hydrogen sources like water into simple sugars and other organic molecules by autotrophic organisms using light or other sources of energy. Most synthetically produced organic compounds are ultimately derived from petrochemicals consisting mainly of hydrocarbons, which are themselves formed from the high pressure and temperature degradation of organic matter underground over geological time scale. This ultimate derivation notwithstanding, organic compounds are no longer defined as compounds originating in living organisms as they were historically. In chemical nomenclature, any organoid group frequently represented with letter R, capital letter R, refers to any monovalent substituent whose open valency is on a carbon atom. For historical reasons, will be discussed in the later sections of this lecture. A few types of carbon-containing compounds such as carbides, carbonates, simple oxides of carbon like carbon monoxide, carbon dioxide, and cyanides are considered inorganic. Different allotropic forms of pure carbon such as diamond, graphite, fluorines, and carbon nanotubes are also excluded because they are simple substances composed of only a single element and therefore are not generally considered to be chemical compounds. The value of the organic compounds is that today's modern life is dependent on the organic compounds. Suppose what you wear, the clothes, the dyes, the hand sanitizers, the paints of the automobiles, and paints of the walls all are made up of organic compounds. Here in this paragraph, you may see that the top three elements on the earth crust are the oxygen, silicon, and aluminum. After the aluminum comes the iron and calcium and sodium. I have not indicated the concentration of carbon as its concentration is less than 0.14%. Beside of the low concentration of the carbon, its importance is vital. Organic chemistry plays an important part in our daily life because food, clothes, paper, ink, rubber, soap, perfumes, medicines, and many other compounds are indispensable to us for proper living. Organic compounds are important constituents of many products, for example, paints, food, plastics, explosives, medicines, petrochemicals, and pesticides. Nowadays, without these modern articles such as plastics, explosives, medicines, and petrochemicals, no one can imagine the existence of modern life. If we talk about the organic compounds, then the first question that comes in our mind is how organic compounds are isolated or prepared. There are two methods by which the organic compounds can be obtained. The first method is based upon the natural resources, that is the isolation of organic compounds from the natural resources, that is from the animal and plant resources. You can isolate and purify the millions of organic compounds from the animal and plant resources. The second option is the synthesis of organic compounds in laboratory. Today, organic compounds of about 10 million has been prepared or synthesized in the laboratory, whereas the inorganic compounds that has been isolated on the earth crust are of 1.7 million different types. In the biochemistry, compounds that are prepared or synthesized by the living organisms are called the organic compounds. However, according to the organic chemistry, its definition is somewhat different. All those molecules that are derived from the hydrocarbons are called the organic compounds. What are the hydrocarbons? Hydrocarbons are the compounds of carbon and hydrogen. The simplest hydrocarbon is the methane. Methane has one carbon to which are attached the four hydrogen atoms through four covalent bonds. The next complicated hydrocarbon is the ethane, and the next to ethane is propane, and so on. So any compound that is derived from the hydrocarbon is called the organic compound. Organic chemistry is the study of compounds that contain carbon or the derivatives of hydrocarbons. It is one of the major branches of chemistry. The history of organic chemistry can be traced back to ancient times when medicine men extracted chemicals from plants and animals to treat members of their tribes. They did not label their work as organic chemistry, they simply kept records of useful properties and uses of things like willow bark, which was used as a painkiller. Their knowledge formed the basis of modern pharmacology, which has a strong dependence on knowledge of organic chemistry. Organic chemistry was first defined as a branch of modern science in the early 80s by John Jacob Berzelius. He classified chemical compounds into two main groups: organic if they originated in living or once living matter, or inorganic if they came from minerals or non-living matters. Like most chemists of his era, Berzelius believed in vitalism, the idea that the organic compounds could only originate from living organisms through the action of some vital forces. It was a student of Berzelius who made the discovery that would result in the abandonment of vitalism as a scientific theory. In 1828, Frederick Waller discovered that urea, an organic compound, could be made by heating ammonium cyanate, an inorganic compound, in the laboratory. Waller mixed silver cyanate and ammonium chloride to produce solid silver chloride and aqueous ammonium cyanate. He then separated the mixture by filtration and tried to purify the aqueous ammonium cyanide by evaporating the water. To his surprise, the solid left over after the evaporation of the water was not ammonium cyanide, it was substance with the properties of urea. Wohler's observation marked the first time an organic compound had been synthesized from an inorganic source. Wohler's discovery was a turning point in science history for two reasons. First, it underdetermined the idea of vitalism because an organic compound was produced from an inorganic one. However, it was represented the discovery of isomerism, the possibility of two or more different structures, ammonium cyanide crystal and urea crystal based on the same chemical formula, that is N2H4CO. Chemists started searching for reasons to explain isomerism that in turn led to theories about the structure of chemical compounds. By the 1860s, chemists like Kekule were proposing theories on the relationship between a compound's chemical formula and the physical distribution of its atoms. By the 19th, chemists were trying to determine the nature of chemical bonding by developing models of electron distribution. So this is the brief history of the organic compounds, how they were synthesized in the laboratory. So the credit goes to Frederick Wohler. In 1828, he synthesized the first organic compound, that is called the urea, from the inorganic source, that is by heating the ammonium chloride and silver cyanide. Here on this slide, I have discussed some of the typical properties of the organic compounds. Most of the organic compounds possess the covalent bonds and they must possess the carbon atom as their structural identity. Most of the organic compounds have low melting points and low boiling points. Majority of the organic compounds are flammable. They are soluble in nonpolar solvents and they may exist as gases, liquid or solids. If I discuss about the three phases, the propane is a gas, it is an organic compound. If I talk about the organic compounds that are found in liquid form, the chloroform is the example of an organic compound that is found in the liquid form. Similarly, acetone is another organic compound found in the liquid form. And if I talk about the solids, then the porphyrin is a solid organic compound. My dear students, this slide is the most important slide that you should have to learn by heart. Always remember, never forget it, that the carbon forms 4 covalent bonds. When carbon makes 4 covalent bonds, its valency is fully satisfied and it has no unshared electrons. Hydrogen always forms 1 covalent bond and it has no unshared electrons. Nitrogen forms 3 covalent bonds and has 1 unshared pair of electrons. When nitrogen forms 4 covalent bonds, it got 1 positive charge on it. So the carbon makes 4 bonds, hydrogen makes 1 covalent bond and the nitrogen may make 3 or 4 covalent bonds. In the case it is making 4 covalent bonds, it got 1 positive charge on nitrogen. Oxygen normally forms 2 covalent bonds and has 2 unshared pairs of electrons. However, oxygen has the tendency to make 3 covalent bonds. In the case it makes 3 covalent bonds, it got 1 positive charge on oxygen. Halogens forms 1 covalent bond and has 3 unshared pair of electrons and hence they can make the 2 covalent bonds, and in the case the halogen makes 2 covalent bonds, the halogen atom got 1 positive charge on it. In organic chemistry, a functional group is a specific group of atoms or bonds within a compound that is responsible for the characteristic chemical reactions of that compound. The same functional group will behave in a smaller fashion by undergoing similar reactions regardless of the compounds of which it is part. Functional groups also play an important part in organic chemistry nomenclature. Combining the name of the functional group with the names of the parent alkanes provide a way to distinguish the compounds. The atoms of a functional group are linked together and to the rest of the compound by covalent bond. The first carbon atom that attached to the functional group is referred to as the alpha carbon, the second is the beta carbon, and the third is the gamma carbon, and so on. Similarly, a functional group can be referred to as a primary, secondary, or tertiary depending if it is attached to 1, 2, or 3 carbon atoms respectively. Functional groups play a significant role in directing and controlling the organic reactions. Alkyl chains are often non-reactive and the direction of the site-specific reaction is difficult. Unsaturated alkyl chains with the presence of functional group allow for higher reactivity and specificity. Often compounds are functionalized with specific group for a specific chemical reaction. Functionalization refers to the addition of functional group to a compound by chemical synthesis. Though routine synthesis methods, any kind of organic compounds can be attached to the surface. In material science, functionalization is implied to achieve the desired surface properties. Functional groups can also be used to covalently link the functional molecules to the surface of chemical devices. In organic chemistry, the most common functional groups are the carbonyl groups. In the carbonyl groups, carbon atom is attached to the oxygen atom through a double covalent bond, and a hydroxyl group that is called the alcoholic functional group, and a carboxylic functional group that is composed of one carbon atom and two oxygen and one hydrogen COOH, and an ester group that is COOR, and an amines NH2. It is important to be able to recognize the functional group and the physical and the chemical properties that they afford to compounds. So what we have learned in this slide, that functional group is an atom or a group of atoms within a molecule that show a characteristic set of predictive physical and chemical properties. Functional group provides a way to classify the organic compounds into families. For example, hydroxyl group is a functional group of alcohol, so any organic compound that possess hydroxyl group may be referred as an alcohol. The functional group determine the chemical and physical properties of compounds. They undergo the same type of chemical reactions and it's a way to name the organic compound. So these are the key points of this discussion. As I have previously informed you that the organic compounds are either hydrocarbons or the derivatives of hydrocarbons. Hydrocarbons are the organic compounds that consist of entirely carbon and hydrogen atoms. We can divide the hydrocarbons into two families, the saturated hydrocarbons and unsaturated hydrocarbons. Saturated hydrocarbons are those hydrocarbons in which the carbon atoms of a hydrocarbons are linked together through a single covalent bond. So the saturated hydrocarbons contains only single carbon-carbon covalent bonds and nothing else. Whereas the unsaturated hydrocarbons are those hydrocarbons that possess double or triple covalent bonds. For example, if they possess a double covalent bonds, they are referred as alkenes, and if they contain a triple covalent bond, they are called as alkynes. Whereas the alternative single and multiple bonds make a characteristic aromatic ring. For example, here on this slide I have shown the molecule of a benzene that has alternative single and multiple bond, that is a double bond here in this case. So you can classify the hydrocarbons either as the saturated or unsaturated hydrocarbons depending upon the type of the covalent bonds found in them. If they possess a single covalent bond throughout the structure, then it is a saturated hydrocarbon, and the saturated hydrocarbons are also called as the alkanes, which is the discussion topic of today's lecture. And if they contain a carbon-carbon double bond, then they are called the alkenes. The alkynes are characterized by the possession of triple bond, whereas the aromatics are usually characterized by the possession of a benzene ring. Alkanes are the hydrocarbons that possess only carbon-carbon single bonds. Hydrocarbons are the simple organic compounds which contain only carbon and hydrogen. If the carbon atoms are linked in chain, the compounds are called aliphatic compounds. If the atoms are linked in ring, the compounds are called alicyclic. The chain compounds or aliphatic compounds may be further classified on the basis of individual carbon-to-carbon bonds. Every carbon atom can form 4 bonds to other atoms, thus the noble gas configuration is reached. That is, 8 outer electrons are achieved. Every hydrogen atom forms 1 bond producing 2 outer electrons, the most stable state for hydrogen. Chain compounds in which all the carbon-to-carbon bonds are only simple single bonds are called alkanes. So listen again, chain compounds in which all carbon-to-carbon bonds are only simple single bonds are called alkanes. The compounds are also called as saturated hydrocarbons. So another name for alkanes is the saturated hydrocarbons, because each carbon-to-carbon bond is a single bond and the valence of the carbon atom is therefore saturated. No more atoms can be bonded to the atom in the compound without breaking the compound into 2 or more fragments. If it contains 1 or more bonds which can react with hydrogens, it is called unsaturated hydrocarbon. Almost all other organic compounds can be named as derivative of these simple hydrocarbons. Alkanes which have long carbon chains are often called the paraffins. The most simplest alkane is the methane, in which 1 carbon atom is attached to the 4 hydrogen atoms, forming 4 single covalent bonds. The next comes the ethane, which has 2 carbon atoms in which the 2 carbon atoms are linked together to a single carbon covalent bonds. The general formula for alkanes is CnH2n plus 2. Simplest alkane is the gas methane, whose molecular formula is CH4. Methane exists as a tetrahedral shape, but it is often represented by a flattened structure, as are most organic compounds. In many cases, the structures can be further simplified without loss of information by omitting all single bonds and writing the letter symbol of the element close to the letter symbol of the element to which it is attached. Thus, the representation of methane as CH4, ethane as CH3CH3 rather than C2H6, and propane is represented as CH3 bonded to CH2 and CH2 is bonded to CH3 rather than C3H8, is representation of a structure as well as the molecular composition. For many simple organic compounds, representations like this are adequate for discussion and identification purposes. When they are not adequate, all organic chemists resort to more elaborately drawn structure which convey the necessary information. The structure of ethane can be derived from that of methane by substitution of a methyl group called the CH3 group for one of the hydrogens of ethane. So if you replace one hydrogen from methane, then the remaining CH3 group is called the methyl group. The structure of propane can be derived either by substitution of methyl group upon ethane or by substitution of hydrogens of methane. The structure of propane can be derived either by substitution of a methyl group upon ethane or by substitution of an ethyl group upon methane. Other methods use the same product, propane. Likewise, the structure of the next member of the series, butane, can be derived by the substitution of methyl group upon propane. The alkane series of compounds can be extended indefinitely by this method. The names of the compounds and their substituent groups are given on this slide. For example, I have given the substituent of methane as methyl and ethane as ethyl. For even longer chains, the name is simply the number given as the Greek prefix. The alkanes above propanes are named by giving the number of carbons in Greek with the ending "ane". If an alkane is not a straight chain, then the longest straight chain in it is used as the basis of names and the shorter side chains are considered to be the substituent. Positional isomerism of alkanes is also found. The two natural sources of alkanes are the natural gas and petroleum. The most important source for alkanes are oils and natural gases. Oil is a mixture of liquid alkanes and other hydrocarbons. High alkanes, which are solid, occurs as residues from oil distillation called tar. One of the largest natural deposits of solid alkanes is in an asphalt lake known as Pitch Lake in Trinidad and Tobago. Natural gas contains primarily methane, about 90 to 95%, with some ethane, propane and butane. Some gas resources deliver up to 8% of carbon dioxide. Traces of methane occur in the Earth's atmosphere. The content in the ocean is negligible due to the low solubility of methane in water. Alkanes are important raw materials of chemical industry and the principal constituent of gasoline and lubricating oils. Natural gas mainly contains methane and ethane and is used for heating and cooking purposes and for power utilities. For transportation purposes, natural gas may be liquefied by applying pressure and cooling it, called the liquid natural gas or LNG. The Sultanate of Oman, for example, exports most of its natural gas as LNG. Methane in the Earth's atmosphere is found mainly due to anaerobic respiration of microbes. The main source of alkanes are petroleum and natural gas found in the crust of Earth. They are formed by high temperature and pressure and under anaerobic conditions from the plants and organisms that were buried long time back. This is why petroleum and natural gases are known as fossil fuels. About 2/3 of the methane produced in nature comes from the reduction of acetate group and about 1/3 comes from the reduction of carbon dioxide and very little amount comes from the reduction of methanol and methylamines. These processes can be achieved by microbes generally known as archaea. Therefore, the essential processes are the conversion of acetate group to methane and carbon dioxide, reduction of carbon dioxide to methane, disproportionation of methanol and methylamine to carbon dioxide and methane. Crude oil can be fractionally distilled to obtain the various products varying in the length of alkyl chain. High fractions can also contain the cycloalkanes. It's it's easy to understand why oil is so important in our lives. Your parents could not drive their car unless it was filled with gasoline or petrol. The school bus could not make it to school without gasoline. Gasoline is made from crude oil. Lubricating oil is also used to keep our automobile engines from getting too hot and to ensure that all moving parts of machinery are kept in good working order. In fact, our world would almost grind to a halt without oil. Factories would stop running, so would cars. Airplanes would be grounded. Tractors on the farms would sputter to a standstill and rust. And people's homes and offices, if heated by oil, would freeze in winter. The kingdom of earth runs on alkanes or runs on oil. The distillation of crude oil is the first step in the gasoline production. Straight-chain gasolines are poor fuels and automobile because of engine knocking and uncontrolled combustion that occur in hot engine. An octane rating or octane number is a standard measure of the performance of an engine or aviation fuel. The higher the octane number, the more compression the fuel can withstand before detonating or igniting. In broad terms, fuel with a higher octane rating are used in higher performance gasoline engines that require high compression ratios. In contrast, fuels with lower octane numbers but higher cetane numbers are ideal for diesel engines because diesel engines do not compress the fuel but rather compress only air and then inject the fuel into the air which was heated by compression. Gasoline engines rely on ignition of air and fuel compressed together as a mixture, which is ignited at the end of compression stroke using spark plugs. Therefore, high compressibility of the fuel matters mainly of gasoline engines. Use of gasoline with low octane number may lead to the problems of engine knocking. In a normal Otto cycle spark ignition engine, the air-fuel mixture is heated as a result of being compressed and is then triggered by the spark plug to burn rapidly. During this combustion process, if the unburned portion of the fuel in the combustion chamber is heated too much, pockets of unburned fuel may self-ignite before the main flame front reaches them. Shock wave produced by detonation can cause much higher pressure than engine components are designed for and can cause a knocking or pinging sound. Knocking can cause major engine damage if severe. The most typically used engine management system found in the automobile today have a knock sensor that monitor if knock is being produced by the fuel being used. In modern computer-controlled engines, the ignition timing will be automatically altered by engine management system to reduce the knock and to an acceptable level. Octanes are a family of hydrocarbons that are typically components of gasoline. They are colorless liquid that boils around 125 degrees centigrade. One member of the octane family, isooctane, or 2,2,4-trimethyl pentane. So one member of the octane family, isooctane, is used as a reference standard to benchmark the tendency of gasoline or LPG fuels to resist self-ignition. Straight-chain hydrocarbons are more prone to induce engine knock than are highly branched compounds. Heptane, a particularly bad fuel, is assigned a base value of 0 octane number, while 2,2,4-trimethyl octane pentane or isooctane has a rating of 100 octane number. The octane rating of gasoline is measured in a test engine and is defined by compression with the mixture of 2,2,4-trimethyl pentane or isooctane and heptane that would have the same anti-knocking capacity as the fuel under test. Alkanes are the hydrocarbons that possess only carbon-carbon single bonds. Hydrocarbons are the simple organic compounds which contain only carbon and hydrogen. If the carbon atoms are linked in chain, the compounds are called aliphatic compounds. If the atoms are linked in ring, the compounds are called alicyclic. The chain compounds or aliphatic compounds may be further classified on the basis of individual carbon-to-carbon bonds. Every carbon atom can form 4 bonds to other atoms, thus the noble gas configuration is reached. That is, 8 outer electrons are achieved. On this slide, you are seeing a molecule of methane. Methane is the simplest saturated hydrocarbon which has tetrahedral geometry. The 4 valence electrons of carbons are shared with the 4 hydrogen atoms, each forming one single covalent bond. On this slide, I have shown the tetrahedral geometry of methane molecule. Methane molecule is the simplest saturated hydrocarbon. You can see that the methane molecule is forming four covalent bonds with the 4 hydrogen atoms, and in this way the valency of the carbon is satisfied or saturated. That is why it is classified as a saturated hydrocarbon. Here the molecule of ethane is represented. I am showing you the tetrahedral geometry and the expanded plain structural formula of the ethane. Actually, the ethane molecule is also exists as in the tetrahedral form. However, for the sake of simplicity on paper, mostly the expanded structural formula are written. The condensed structural formula is also shown here. Here you may see the detailed bonding of the methane molecule. The carbon atom, the central carbon atom of the methane is forming 4 sp3 hybridized orbitals which overlap with the 1s orbital of hydrogen, thus forming 4 sigma bonds that are oriented at 109 angstrom at 109 degree. So the overall geometry of the methane molecule is tetrahedral. Here on this you may see that the bond angle is about 109 degree. The alkanes can exist as gas, liquid or solid at room temperature. The unbranched alkanes, methane, ethane, propane and butane are gases. Pentane through hexadecane or liquid, the homologous larger than the hexadecane or solid. Branched alkanes normally exhibit lower boiling points than the unbranched alkanes of the same carbon content. This occurs because of the greater van der Waals forces that exist between molecules of the unbranched alkanes. These forces can be dipole, induced dipole or induced dipole in nature. The unbranched alkanes have greater van der Waals forces of attraction because of their greater surface area. Solid alkanes are normally soft with low melting points. These characteristics are due to strong repulsive forces generated between the electrons on neighboring atoms which are in close proximity in crystalline solids. These strong repulsive forces counterbalance the weak van der Waals forces of attraction. Finally, alkanes are almost completely insoluble in water. For alkanes to dissolve in water, the van der Waals forces of attraction between the alkane molecule and water molecule would have to be greater than the dipole forces that exist between the water molecules. This is not the case. So the key point of the boiling point and the melting points of alkanes increases as the size of the alkane increases. The rise in the boiling point is due to the increased attraction between the molecules which increase as molecule size increases, accounting for the higher melting and boiling points of larger alkanes. Here you may see that the chain branching always results in the lowering of boiling points due to the increase in the compactness and the decrease in the surface area of the alkanes. So as the chain branching is increasing, the lowering of boiling point is observed due to the increase in the compactness and the decrease in the surface area. Alkanes are non-polar solvents. Since only carbon and hydrogen atoms are present, alkanes are non-polar. Alkanes are immiscible in water but freely miscible in other non-polar solvents. Alkanes consisting of weak dipole-dipole bonds cannot break the strong hydrogen bonds between the water molecules. Hence, it is not miscible in water. The same character is also shown by alkenes. Because alkanes contains only carbon and hydrogen, combustion produces compounds that contain only carbon, hydrogen and or oxygen. Like other hydrocarbons, combustion under most circumstances produce mainly carbon dioxide and water. However, alkanes require more heat to combust and do not release as much heat when they combust as other classes of hydrocarbons. Therefore, combustion of alkanes produce high concentration of organic compounds containing oxygen such as aldehydes and ketones when combusting at the same temperature as other hydrocarbons. So the key points are alkanes are non-polar compounds. Their solubility may be predicted by like dissolved like rule, which means non-polar compounds are soluble in non-polar solvents and polar compounds are generally soluble in polar solvent. So the alkanes are insoluble in water. Here on this slide I have summarized the physical properties of the alkanes. The number one, these are the non-polar and insoluble in water. They have lower density than the water. That is why the gasoline floats on the surface of water. Low boiling point and melting point. They have the low boiling and melting point gases with 1 to 4 carbon atoms. All those alkanes that have 1 to 4 carbon atoms exist in the form of gases. Those alkanes that have 5 to 17 carbon atoms like kerosene, diesel and jet fuels, they exist in the form of liquids. All alkanes that have carbons more than 18 exist as the solid. For example, wax, paraffin and vaseline, etc. So the thumb rule is, as the number of carbon atoms in alkanes increases, their boiling and melting point increases. As the number of branches in alkanes increases, their boiling point and melting points decreases. Here on this slide I have shown the N-butane and isobutane. So the isobutane have no boiling point and melting point than the N-butane. How one can name an alkane? The name of an alkane consists of two parts, the prefix and an ane. If it contains one carbon, the prefix is meth and the ending of the name is with ane. So the name becomes methane. And if it contains the two carbons, then the prefix is eth and the ending is with ane. So the name becomes ethane and so on. So here is the repetition of your syllabus that you studied in FSC Part 1 or 2. The main purpose of this slide is to show you how we can write the propane. You can write the structural formula of the propane as CH3 bonded with the single bond to CH2 and the CH2 is bonded to a CH3 with through a single bond. So it is a propane. Or you can, line angle formula may also be used to represent the propane. Here each corner is representing a carbon which is fully satisfied with the hydrogen atom. So here I have represented the line angle formula of butane and also I have shown the structural formula of the butane. So butane is represented in the normal way as well as in the line angle formula, and similarly I have represented the line angle formula of the pentane. Here each corner is representing a carbon that is fully satisfied with hydrogen atom. In IUPAC system, if you remove a hydrogen from an alkane, the remaining group is called the alkyl group. So you have to add the "al" at the end of the parent name of the alkane. For example, from the methane, we have cut the "ane" and represented and replaced it with "yl." So the methane becomes the methyl, and similarly ethane becomes the ethyl, and propane becomes the propyl. And similarly, the other substituents such as fluorine, chlorine, bromine, and iodines are represented as fluoro, chloro, bromo, iodo, etc. The first step in the naming of an alkane is the selection of longest continuous chain. So here in this example, I have selected a longest continuous chain which comprises of 4 carbon atoms. So the parent name of the longest chain is the butane. Then I will start the numbering from that side from which the substituent got the lowest number. So in this example, the substituent comes at the carbon number 2. So the name of the molecule is 2-methyl butane. On this slide, I have shown the tetrahedral geometry of methane molecule. Methane molecule is the simplest saturated hydrocarbon. You can see that the methane molecule is forming four covalent bonds with the 4 hydrogen atoms, and in this way the valency of the carbon is satisfied or saturated. That is why it is classified as a saturated hydrocarbon. How one can name an alkane? The name of an alkane consists of 2 parts, the prefix and an ane. If it contains 1 carbon, the prefix is meth and the ending of the name is with ane. So the name becomes methane. And if it contains the 2 carbons, then the prefix is eth and the ending is with ane. So the name becomes ethane and so on. So here is the repetition of your syllabus that you studied in FSC part 1 or 2. On this slide, I have given the 2 molecular structural formula of 2 compounds. The first one is of 2,4-dimethylpentane, which is representing, this name is representing that at the 2 and 4 number, 2 methyl groups are present, whereas the backbone or the longest continuous chain comprises of 5 carbon atoms. Similarly, the second formula is of 3,5-dichloro 3-methylpentene. I have represented the 3,5 together, or since they are the similar substituent, that are the chloro groups. So 3,5-dichloro means at the 3 and the 5 number carbon atoms are present the chloro substituent, whereas I have again represented the 3, which means that a different types of the substituent is also present on the 3 number carbon atom, and which is a methyl. And here the longest continuous chain consists of 7 carbon atoms. So its name is the 3,5-dichloro-3-methyl-heptane. So the question is, how do we name the cyclic hydrocarbons having one or more than one substituent? Use the prefix cyclo plus the name of the open chain alkane. If it has one substituent, there is no need to represent the location of the substituent. For example, in the On the left side, you may see the structure of the chlorocyclohexane. I have not written the one chlorocyclohexane because it is understood that the chloro is present on anywhere on this cyclohexane. So in the case of in the second example, that is shown in the middle one, that is of 1 bromo 2 methyl cyclohexane. The bromo is given the lowest number because bromo starts with B and the methyl starts with N. So the bromo is given the lowest number on the basis of the arrangement of alphabets. For in the third example, we have started the numbering from the chloro because chloro starts with the C. So the chloro gets in this way first number 1 chloro, and then comes the 2 is the nitro, and 3 is the hydroxyl. So we have to write the name of the substituents in the alphabetic manner. So 1 chloro, 3 hydroxyl, and 2 nitrocyclopentene is its correct name. Alkenes and alkynes on catalytic hydrogenation give alkanes. Catalyst nickel is used in finely divided form. If palladium or palladium are used as catalyst, reactions occurs at narrow temperature. Also, sometimes nickel is used as catalyst. It is obtained by boiling nickel aluminum alloy with sodium hydroxide when aluminum dissolves, leaving nickel in finely divided states. The filtered, washed and dried nickel is known as Rene nickel. Rene nickel is effective at room temperature and atmospheric pressure. If you are using nickel as the catalyst, you need elevator temperature in the range of 200 to 300 degrees centigrade, whereas the use of the palladium and palladium lowers the temperature needs. Whereas there are Rene nickels, with the Rene nickel you may accomplish the hydrogenation of alkene or alkanes at the room temperature and normal atmospheric pressure. Again, on this slide I am showing the Sabatier-Sandern reduction method, or the hydrogenation of alkyne. The acetylene upon hydrogenation gives the ethane. Alkyl halides on reduction with nascent hydrogen form alkanes. For example, the question is how the nascent hydrogen can be produced. There are several ways by which you can produce the nascent hydrogen. One is the reaction of zinc with hydrochloric acid, or you may react the zinc with acetic acid, or you may use the zinc copper couple in ethanol for the production of the nascent hydrogen, or red phosphorus and hydroiodic acid may be used to produce the nascent hydrogen. Another method is the use of aluminum amalgam in ethanol. Alkyl halides can also be reduced catalytically to alkanes by hydrogen with palladium or lithium aluminum hydride, or by hydrogen with nickel catalyst. The yields are generally high and the hydrocarbons are formed in high concentration. It's easy to understand why oil is so important in our lives. Your parents could not drive their car unless it was filled with gasoline or petrol. The school bus could not make it to school without gasoline. Gasoline is made from crude oil. Lubricating oil is also used to keep our automobile engines from getting too hot and to ensure that all moving parts of machinery are kept in good working order. In fact, our world would almost grind to a halt without oil. Factories would stop running, so would cars. Airplanes would be grounded. Tractors on the alkanes are synthesized by heating an alkyl halide with sodium metal in dry ether. Two molecules of alkyl halides combine to afford an alkane having an even number of carbon atoms. However, the wood synthesis has some limitation. Number one, methane cannot be prepared by wood synthesis. Number two, it always gives even number of alkanes. So the odd number alkanes cannot be prepared with this method. Number three, the reactions involving the use of tertiary alkyl halides fails to give the wood synthesis. So in wood synthesis, tertiary alkyl halides cannot be used. when sodium salt or carboxylic acid is heated with soda lime, which is a mixture of sodium hydroxide and calcium oxide, alkane is obtained having one carbon less than the salt by the removal of a molecule of carbon dioxide. This reaction is also known as decarboxylation reaction. For example, when sodium ethanoate is heated with soda lime, methane gas is produced. Cold electrolysis is another method for the synthesis of alkanes. A concentrated aqueous solution of sodium or potassium salt or carboxylic acid on electrolysis form alkanes containing even number of carbon atoms at the anode. Alcohols, aldehydes and ketones may also be reduced to produce the alkanes. For example, alcohols upon reduction with red phosphorus and hydroiodic acid at 200 degrees centigrade produce the alkanes. Similarly, aldehydes can be reduced with the same reducing agent, that is with red phosphorus and hydroiodic acid at 200 degrees centigrade to produce the alkane. Similarly, ketones may also be reduced to produce the alkanes with the same reducing agent. Today we have learned alkanes are the saturated hydrocarbons which are characterized by the possession of carbon-carbon single covalent bonds. These may be isolated either from the natural resources or may also be synthesized in the laboratory. The natural sources of alkanes include the crude oil and the natural gas. In the laboratory, these may be prepared from the alkenes, alkynes, alcohols, aldehydes, ketones, Greek nitrogen, and from the alkyl halides. So your assignment or the task is that you have to synthesize the N-butane, 2,3-dimethyl hexane and isobutane by 8 different methods. So you have to synthesize these 3 alkanes by 8 different methods. I am waiting for your response. At the end, here is a list of the recommended books that you may consult for the preparation of your lecture.